All right, so everybody's favorite, how to do the calculations after to figure out your original cell density when you do the viable plate count. Okay, so this is just, remember, this is what you would have done in lab. You take your numbers here, they grow up to extrapolate back to what's in your original stock culture. Okay, I'm going to come back to this slide in a minute. But first of all, I want to talk a little bit about dilution theory. Okay, like I mentioned last time, this is a good life skill to have, really even apart from this lab. When you're trying to make a particular dilution, your dilution is going to be equal to your input volume, and they go through this in your lab manual as well, divided by the total volume. Okay, so that's really important. So for example, you have, say, original stock culture of bacteria that say you want to dilute 1 to 10, right? The easiest way to do that is to take out 1 ml and add it to 9 mL of some diluent. In class, we use sterile saline. Okay, so 1 ml, this is your input right here, and then your total volume that you put it into here is 1 plus 9. Okay, so that's going to give you a 1 to 10 dilution. Sometimes we write that as a fraction. You can write it as a ratio. We could also write that 10 to the negative 1. That just means all the same thing. That means the inverse of 10, basically. Okay, so that's the easiest way to make a 1 to 10 ratio. Of course, the biggest mistake that we want to make is to say, oh, take out 1 ml and put it in 10 mLs. No, that would be a 1 to 11 dilution. Okay, so let's say you have a stock culture and I ask you to make a 1 to 5 dilution. Again, a lot of different ways you could do that, but easiest way, take out 1 ml, put it in 4 mLs of diluent, and that's going to give you a 1 to 5 dilution. Okay, what if we wanted to dilute our stock culture and wanted to make a 1 to 100 dilution? Well, you could take out 1 ml and have a great big flask and put it in 99 mLs of diluent. That would give you a 1 to 100. But in our case, in lab, we only need 1/10 of a mil of this. So we're going to be wasting all sorts of media. We don't want to do that. We could take out 0.1 mil and put it in 9.1 divided by 10. That's the same thing as 1 to 100. Okay, but what we're actually going to do is make some serial dilutions. So like we outlined before, we have a stock culture. Usually we use E. coli, okay, and we're going to make a serial 1 to 10 dilutions. Okay, so we take out 1 ml, put it in 9 mLs of diluent, that's a 1 to 10. Okay, and then we're going to do a 1 to 10 of a 1 to 10. So how do you figure out what the dilution here is? You multiply. Okay, again, we're going to make a 1 to 10 dilution of a 1 to 10, so that's going to be a 1 to 100. If we make another 1 to 10 dilution, we're making a 1 to 10 dilution of what's in this tube, a 1 to 100. So this is going to be a 1 to 1,000. Hopefully you're getting the idea here. We're making a 1 to 10 of this tube, that's a 1 to 1,000. So 1 to 10 times 1 to 1,000, this is 1 to 10,000. And one more time, a 1 to 10 of a 1 to 10,000. This is going to be a 1 to 100,000 dilution. Okay, so you can see why it gets a little bit easier to use this notation. This is a 10 to negative 1. This is a 10 to negative 2. 10 to negative 3. 10 to negative 4. 10 to the negative 5. Dilution. Okay, so then we have to figure out, the reason, remember, we do these dilutions is because we don't know which one is going to give us a countable range. If we knew that, we could just kind of dilute it all at once and it could be easy. But we're going to take out 1/10 of a mil, remember? And with that spread plate technique using a glass hockey stick, very technical term, on our tryptic soy agar. Okay, spread that around, incubate, and then count the number of colonies that grow up the next day. All right, we're looking for, remember, a countable range between 30 and 300 colonies. So let me give you an example of some actual numbers. Remember, when we only dilute it a little bit, probably these are going to be too numerous to count. Let's say we count 214 colonies on this plate, 28 on this one, and 3 on this plate. Okay, so remember, change colors here. We're looking for between 30 and 300. So if I give you numbers like this, you're just going to ignore that. Okay, you're not going to use those two dilutions to do your calculation because that's not considered statistically significant. Okay, the formula that we give you in the book, and I'll try to help you think through this without the formula as well. Your original cell density is equal to the number of colonies on the plate divided by the mils plated. Multiply that by 1 over the dilution. Okay, so notice the volume that's in this dilution here, that doesn't make any difference. And our answer is going to be per mil, so it doesn't really matter how much volume is in your stock culture as well. If you knew you had 10 mils there and your answer was per mil, you could multiply by 10 and then get your total numbers there if you want. All right, so we're going to use this plate here and this corresponding dilution because this is in our countable range. All right, so using those numbers, we got 214 colonies. The mils plated, that's how much we took of our dilution and put it on our agar plate. So in this case, remember, just a drop or two, 0.1 mil. You could use a larger volume there if you did not do a spread plate, if you did something called a pour plate, where you actually added the volume right into the liquid media and then let it harden. But we have to use kind of a small amount if we're going to just put it on the surface of the plate there. Okay, and then you're going to multiply by 1 over the dilution. And here's our dilution, 1 to 1,000. Make sure you keep this 1 here, 1 over 1,000. I know that seems a little bit cumbersome. If you actually just put 1 over 1,000 here, that's going to give you a really small number for your original cell density, less than 1. So think about it, that wouldn't make sense if you got 0.2 for your original cell density. That's less than 1 cell. Okay, this is going to be a really big number, thousands, maybe even millions. Okay, so to do the math here, this is the same thing as multiplying by 1,000, when you get 1 over 1,000. All right, so that makes it a little bit easier. You add the zeros there. And when you divide by 0.1, that just adds another 0 on the top. So you can do these 1 to 10. If it's just simple 1 to 10 dilutions, you can do that without a calculator. I would encourage you maybe use a calculator to begin with or understand how to use your calculator, but sometimes students get goofed up when they use a calculator too. So about 2 million cells, you can change that to scientific notation if you like, 2.14 times 10 to the 6th. Every once in a while, I have a student say, oh, this is a negative exponent. Remember, that's going to be way less than 2. Okay, so, whoops, that was cumbersome there. Remember, it's a big number, so about 2 million. Units. Our units here are going to be colony-forming units per mil. Now, you would think that it would be cells per mil, because isn't that what we're trying to figure out, how many cells are in this original sample? Well, a colony-forming unit is defined as a cell, or let's say a clump of cells that grows into a colony. Okay, so remember I mentioned in the last video that some cells, especially say Staphylococcus, for example, they tend to clump together. So that clump may have actually grown into a colony here instead of a single cell. So when we use these units, colony-forming units, that reminds us that this number that we got may actually be a bit of an underestimation if you have a species of cell that tends to clump together. Now, E. coli, which we usually use for this lab, doesn't really clump together all that much, so that might not be an issue. But that's the reason that we say colony-forming units instead of cells. So a colony-forming unit could be a single cell, it could be a little cluster of cells. Whatever it is that grows into the colony on this plate. Let me give you a practice problem, and we'll go back up and utilize this original diagram here. So I'm going to give you some numbers here that don't work out quite as easy, and see if you can still make the calculation. You're going to need a calculator here for this. So we've got some stock culture that you're trying to figure out the original cell density. Okay, so given that you're taking out, and let's see, this tube, you're taking out 2 mils and putting it into 8 mils. Okay, we're going to do that a few times. Okay, just ignore this last one, we don't need that. And then of the dilution that's made, you're going to take out 3 mils to plate it. Okay, and then let's pretend, let's see, these two are too numerous to count. This plate is 296, and here we count 11 colonies. All right, so pause it. I would encourage you to pause it and try to work this out yourself, and give you some time, see what you come up with. Okay. All right, let's say, remember our equation, original cell density equals number of colonies divided by mils plated times 1 over dilution. All right, I haven't given myself very much room to work this out, so let's see if I can make my tip a little finer here. All right, so first of all, ignore this one, right? Change here to red, because this is not in the countable range. Sometimes I might say, oh, you counted 500 colonies here. Okay, ignore that. If there happen to be 2 different plates that were both in the countable range, then you could figure out the original cell density of those two plates separately. Say if this was 31 instead of 11, and then average those original cell densities. Some argue that it would be more correct to use this number because it's been manipulated less pipetting, less chance of error. Right, so either one of those ways would be correct in my mind. Typically, I just give you, in problems like this, I just give you one that's in the countable range to make it easier. But make sure you pick the right one. All right, so let's say we have 296 colonies, and then we get to divide by the mils plated. So in this example, that was 3 mils. Multiply by 1 over the dilution. Well, we have to figure out now what is the dilution of this tube. Let's start here, the first tube, and work our way over. All right, so the input volume here is 2 mils and a total volume of 2 plus 8. So the dilution here is 2/10, and let's reduce that fraction, 1/5. So this is a 1-to-5 dilution of our original stock culture. All right, and then we're making a 1-to-5 of a 1-to-5. So multiply those. This is a 1-to-25 dilution. I said you were going to need your calculator. And then we're making a 1-to-5 in this tube of a 1-to-25. Okay, so this tube is a 1-to-125 dilution. Okay, and of course this one would be a 1-to-625, 1-to-5 of a 1-to-125. But again, we don't need to worry about that. All right, so our dilution here is 1/125. All right, so doing the math there, that's going to be the same thing. Remember, you multiply across. Let's flip this to be 125. Don't forget this. So that's going to give us, let's see, 37,000 divided by 3. And that equals about 12,000. It's a little on the low side. I just made up these numbers, obviously. Remember your correct units, colony forming units per mil. Okay. Another way, maybe you're bad at remembering formulas, because if you saw this on an exam, I wouldn't be helping you by giving you this formula. If you can just remember, hey, I'm going to take my number of colonies and I'm going to divide that by the dilution. Okay, so in this case, that's going to give you 296. Our dilution here, remember, was 1/125. So I multiply 296 by 125, and that gives me 37,000. But then you have to remember, I want my answer per 1 mil. Okay, this answer is per 3 mils. So I have to divide by 3, and then that's going to give me the same answer as before. Okay, so if you only take out 1 mil here and put it on your plate, that makes your calculation a whole lot easier. You don't have to take that second number into account. Okay, so don't be afraid to see me or I guess ask me. I can give you some more practice problems because you will probably see something like this on an exam. So just don't be afraid to ask. I know sometimes the math comes easy to people, sometimes not. Okay, thanks for listening.